Yeah. So, welcome to 1300. This is the first workshop. So, my name is Henry. That's my ZID. So, I'm quite ancient, but surprisingly, I'm still an undergrad. I'm just my 5th year, finishing off my research thesis. I'm doing civil engineering, probably like a lot of you, but some of you guys might be mech engineers, electronic, aerospace, all that stuff. Yeah, for those of you guys who came in a little later, I'll just re-explain what that stuff is on the board. So I take my notes digitally. It's gonna move around a bit like this. That's on my tablet. And the way these lessons are kind of structured is I'll run through a bit of theory. I like to use something called Kazoos, which is like Kahoot basically. It's just a way to I guess it's like test your understanding a bit. It's a bit more interactive rather than me just yapping at you. And then I've included just like a bunch of notes in the course, and then we'll run through some worked examples once you've sort of understood it at that level. But in terms of the QR codes at the bottom that you see here, the one on the left is the attendance form. Scan that, fill it out. It's got a bit of optional feedback if you like. You can just fill that out at the start or the end. If you ever come late and you miss it, you can just tap me on the shoulder, scan the attendance whenever you're in. And then the QR code on the right is my notes, which will bring you to the Google Drive with this stuff on it. So if you look on the Google Drive right now, it'll say work in progress notes, because more often than not, I'll make a mistake. So sometimes I like to update it. And so when it doesn't say work in progress anymore, that's when it's finalized. But yeah, just a bit of background from me in terms of teaching. The first time I taught was this very course last year in term 2, and I really like the course. I really like teaching, and this is my 3rd time teaching it now. I taught it in the summer as well. Yeah. Anyway, without further ado, I'll just get started. Has everyone got those QR codes up? If not, I'll just keep yapping for a bit longer while I'm doing that. But yeah, the other thing to note is that I'm actually recording these, and then probably starting from next lesson, I'll have like another QR code to access the recordings. So if you ever miss out on any of these recordings as well, yeah, you can always look back at it, especially later in the course once you've forgotten the earlier stuff as well. Okay, so I'm just going to assume everyone's gotten those yet. Now, so the first thing I've done is I've just broken down the course in terms of the very basics. So I haven't gone into details, but I like to do tree diagrams because, I don't know, it's very visual. It's very easy to see kind of where this course is going. So the course is broken up into statics and dynamics, right? And the first part we learn about is statics. So where statics and dynamics comes from is Newton's laws, which you've probably heard about in physics. A couple of you guys might have done engineering studies in high school, which will help a lot with this course as well. But the statics half is based on Newton's first law, so that's sum of the forces is equal to 0. That's basically when things aren't moving. So this is really useful for like buildings, bridges, when engineers are designing structures. It also is useful for example, like for water engineers if they want to design a dam. Even though that's in the water discipline, the dam's still not moving. So yeah, you'll use these skills throughout your entire degree. Even if you're not a civil engineer, you'll use these skills a lot. Yeah, so I like to just cover the basics. Again, most of you guys know what forces are, but we'll run over it in this lesson. Some of you guys might not know what moments are actually, and that's probably those of you who haven't done engineering studies in high school, which actually just check your hand up if you've done engineering studies in high school, because that will let me know like how fast I should go. Check your hand out. All good. How about those of you guys who've done physics in high school? I'll just check your hand out. It's okay if you haven't. But yeah, sorry. Okay, cool. Next, then we'll like move on to structures, which again is under statics. Structures is a big part of this course because that's kind of where it's going for civil engineers. Like this course is the basis for that essentially. You'll learn about let me just get in that part you'll learn about beams, trusses, frames. You'll get pretty familiar with these words as we go. And then basically from week 7 onwards, we move on to dynamics, and that's broken up into particles and rigid bodies. And those are just types of objects. I'll touch upon this a bit more probably next workshop when we talk about moments a bit more. But yeah, you've probably heard the words kinematics. Oh yeah, kinematics and kinetics in the context of physics, but I'll tell you them in the context of particles and rigid bodies as well as we progress through the course. Okay, so that's an overview of the course. We're just going to keep going. The first thing to note, I suppose, like, because I've kind of trialed and errored like how to teach this course best over my experience teaching in term 2 last year and then summer. But the first thing I realized that should be taught is compression and tension. So essentially, just having a look at my whiteboard marker, there's two types of axial forces. This is just, okay, basically there's compression, which is if I'm pushing this together, pushing this marker together, that would be compression. And then the other type is tension, so that's pulling it apart. So this is important because a lot of the time what we're analyzing in this course are straight lines. That's like beams, which we can approximate as straight lines. That's like rods, like this marker. And so, yeah, very often you'll have to think about how compression and tension work. And for example, a rope. A rope is essentially just a line, right? And for a rope to function, it needs to be in tension, right? It basically doesn't do anything in compression. It acts like spaghetti or whatever. Another example, there's not really one in this room, but pretend there was a big column in the middle of the room. So like from the floor to the ceiling. It's taking gravity loads, right? So that's all in the vertical direction. And it's actually going to be compressed. That column would be in compression. That would be an example. Let's see. Like projector. There's like some sort of steel member holding up that projector, right? Projector's heavy. That's in tension. So it's being pulled. So you should try to get like a good holistic understanding of these two concepts because it's the foundation of what we're going to be talking about next. Okay. So just to quickly draw it in terms of arrows, because forces are essentially vectors, right? And so they can be drawn like arrows because they've got a magnitude and a direction. So compression, the forces on a member in compression would look like that. And tension, the arrows would be like that. They're just pulling apart, right? Okay. The other thing to note about compression and tension is there's something called these members here are called two-force members, and that just means they're either in axial tension or compression. Yep, that's just jargon, but you'll come to learn that, I think. Either you've learned that in the lectures already, or you'll learn it next week or something. It's in an early part of the course. Okay, any questions so far? Is that okay? Okay. So, let's break down the formulas in this first part of the course. Oh, actually, wait. Okay, sorry, before we do that, I'm going to quickly quiz you guys, all right, on what we just said. Hold on for a sec. Should bring me into the right thing. All right, so how this is going to work is if you pull out your phone, you're going to see a QR code very shortly. Oh my God. Bear with me, guys. Shuffle question is off. Okay, great. Okay, so we start this. Basically, this QR code is gonna just quickly quiz you guys on what I've been saying. And yeah, it's pretty easy this week, but it's gonna go harder and harder as we go. But yeah, no, not really any calcs. It's just understanding. So loud. Okay. Tom, do you have any water? Can you run with this? Wait, do you actually know where? You get downstairs, you see that downstairs okay, good. Alright, is everyone in? Still waiting? Okay, great. Alright, we're gonna get started, yeah? This one should be very short. Okay. Let's look at the questions, all right? Okay, so, yeah, normally how this goes is in the early weeks, everyone's feeling great, and then just dips down after that. But, you know, it's not too bad so far, I'll say. Okay, cool. Okay, so yeah, I was just quizzing this because I wanted to get an idea of the room. I think a lot of people do this course in term 2 because I've heard it's easy, which I'll say, yeah, it's easier than the other terms in Edge 1300, which is kind of fair enough. But in terms of my background and in terms of how I'll be teaching it and the perspective of it, I'll mainly be able to give examples from civil engineering. So if you're doing civil engineering, then I'll have more examples of that for you. But every now and then I'll sprinkle in aerospace, mechatronics, that kind of stuff, particularly in the dynamics half, because civil engineers deal with dynamics a lot less. Okay. Okay, so basically, oh well, we all got that right. So I don't think I need to explain it. But there are a few words here which you'll see pop up soon. Particularly bending moment and torsion, you'll see starting next week. So these are types of moments, right? Yeah, I don't want to get into it yet, but we will find that out next week, basically. Okay. So a column, that's supporting the roof, right? So say there's a column in the middle of the room. This is in compression because gravity acts downwards, and the self-weight of the column kind of will have gravity forces acting throughout it, and then it will be compressed, essentially, right? Oh, sorry. See, the thing is, I didn't go over, I forgot what was in this. Okay. Probably should have done the formulas and then just get it. Come in. Okay, well, now that we're here, we'll start talking about this, and then I'll transition this to the formulas part. So probably the people who got this more correct were the people who've either done engineering studies before or have watched lectures or something. But unit vectors, they're kind of like building blocks in certain directions. And what orthogonal means is at right angles. So I and j conventionally are used to denote the x and y directions, respectively. Sometimes you'll also see a unit vector of k direction. That'll represent the z coordinate or whatever if you're looking at a 3D system. But more often than not in this course, you won't be dealing with 3D coordinate systems. You'll be dealing with 2D ones at some point. Yeah, this comes up in rigid bodies towards the end of the course. And you'll be using relative vector question. Yeah, anyway, you'll see this. Sorry, I should have done this in the other order, so just kind of stitch you up. Okay, they're not, something to note down though is that they're not necessarily important for solving every type of question. In fact, I don't really use unit vectors until the dynamics portion of the course where it calls for it, because I find them slightly more complicated than using force components, which is the other type that you'll see. Okay, so instead of just explaining this with nothing to show, I'm just going to show you it with my formula sheet. So, okay. Basically, here's the way it works, okay? So this week's focus is on forces, and there's 3 things to point out first about forces. These things might seem obvious, but it's just good to reiterate first. The first thing is that it's a vector, which is different to a scalar, right? So vectors will have a direction, and they'll have a magnitude as well. Whereas a scalar quantity like mass, for example, that would only have a magnitude, right? The other thing is that forces are physical quantities, and that's kind of what differentiates this from something like pure maths, where it's not bound to an actual physical concept in real life. And in particular, the units that you'll see a lot pop up in the course are newtons, named after Newton, of course, and then kilonewtons, which is 1,000 newtons. So yeah, you'll see it depending on the context. Usually buildings will support large loads, and then you're going to be working in the scale of kilonewtons. Maybe a small scale kind of machinery that you see might be in newtons, for example. So you'll see both, but you should be able to fairly comfortably convert between those 2 units. Okay, what I was talking about, sorry, is that you can express a force in terms of a magnitude and an angle, right? So that's the whole magnitude and direction thing I was talking about. Maybe on a Cartesian plane, it would look something like this, right? When you see F surrounded by the absolute value notation, that's referring to its magnitude. So what's the magnitude of this force? Yeah. So let's say that's 200 newtons, whatever. And it will also have some kind of angle. And so here I've decided to do it an inclined angle from the horizontal x direction, in the positive direction. But yeah, visually I've notated that angle, so you don't need to. Sometimes you'll be doing questions in terms of like compass directions. Sometimes you'll say like north, east, south, west. Then the angle is relative to those kind of compass directions instead. But here I've just notated it as such. Okay. So in terms of the unit vectors, as I was saying before, these are like your building blocks, right? And so they're going to have something like, okay, I've decided to do 1,000 building blocks in the I direction. So the I component only is talking about the direction component. And then the J is also only direction, but in the Y direction. And if we have a negative J vector, that's referring to downwards, right? So, sorry, I should probably draw this out. So like, that's the J direction, sorry, that's the I direction, that's the J direction. Basically, we're referring to 1,000 I that way and 400 J acting down, right? If it's negative magnitude. But the important thing to keep in mind is that this has to be like I and J aren't bound to a physical kind of quantity. So that's where the newtons come in, right? So the newtons make it a real physical thing. Makes sense. Yeah. sorry, I always struggle explaining this particular topic because it's kind of abstract. It's easier to see like in the actual questions. But if anyone has any questions right now, I can try and answer them as well. Yeah, sorry. Okay, let's talk about force components quickly. So, basically, right, if we're working with a 2D coordinate system that's based on the XY plane, right, we can break this down. This basically diagonal kind of force vector that we have into its horizontal component and its vertical component. So we call that fx and fy respectively, right? So if I'm ever saying like, oh, what's the horizontal component of this? What's the vertical component of this? It just means what's the magnitude of this diagonal arrow, but only that particular portion of it, if that makes sense, right? Yeah. Okay. Converting between these things. So here's where the formulas kind of come in. So all I've done is I've kind of just said, okay, there's two ways to express these forces, right? So how do we convert between these things? Let's start with converting from unit vectors over to magnitude and angle, because sometimes you have to do that, right? So we get this. Basically, to convert to your magnitude, we use Pythagoras theorem. So that's what I was talking about in the quiz. Okay, we use Pythagoras theorem because if you think about it, let me just redraw this a little nicer. We have our horizontal component of our force, right, like this. We've called that fx, right? And then we have our vertical component as well, so that's our fy. So if we want this diagonal magnitude, that's just Pythagoras, right? That's just a right angle triangle, like that. And yeah. Okay, the other thing is that, say you want to go from unit vectors to find the angle, say that angle here, this one, that angle there. Maybe it's nicer to look at this example first, right? So, okay, sorry, just focusing on this particular case. Oh, what's going on? Focusing on this particular case here. What we do, here's how I remember it. Tan inverse rise over run. Okay. Yes, so this, right? Okay. The reason is because if we have tan theta, that's your opposite over adjacent in terms of your right angle triangle rules, right? We were just solving for theta. That's what we're interested in. So what we do is we move tan to the other side, and that gives us the inverse, right? That's how we get that formula from. So the opposite side is that y component, right, of that diagonal arrow, and then the x component is the adjacent side. So that's where it comes from. Yeah, we'll talk about that as we do the question a bit more. Hopefully that kind of makes sense. Okay, cool. What about converting the other way? Sorry, I've really made a mess here. Let's move that a bit. I'm going to do this maybe in green. Okay, so say you want to convert now from this magnitude and this angle that you have back into unit vectors, right? Or maybe you just want it into unit vectors to begin with. So we want this component and this component. We want to find the fx or that fy component of that diagonal arrow, right? So then we have to use our trigonometry, basically, right? We can use the magnitude multiplied by cosine theta, that's sine theta for these, right? But you got to be a bit careful with these because it really depends on what kind of angle you're referring to here. So here, this is really dumb, right? But like, this is the way that I learned like the unit circle when I was like in year 9 or whatever it was. This is the unit circle, right, from maths. I call these the butterfly angles because it looks like a butterfly, right? So if you're working with these butterfly angles, that's when you're allowed to use these particular formulas, right? But if you're working with the, I don't know what you'd call this, hourglass kind of angles, right? I'm talking about this shape here. If you're dealing with this hourglass kind of angle, let's call them alpha or something, then these would be swapped around, right? Yeah, does that make sense? Okay, just make sure you don't get them mixed up because it's really easy to get them mixed up, right? Okay, cool. That pretty much does it for this first part, right? We'll also talk about resultant forces quickly. Okay, so basically, with forces, there's two things you can kind of do. Actually, wait, before I get into that, what I've written on the right here is kind of based on converting between unit vectors and magnitude and angles, right, that I've done earlier. So I'm just going to mainly focus on this picture on the left, actually. Okay, so imagine you have this hook that's anchored to the wall, and so it doesn't move. We call that supported, where we assume that it doesn't move at all. And you have 3 ropes coming off of it. Ropes are in which type of force action? Ropes are in tension, right? So there's 3 ropes, they're in tension, they're pulling off of this anchor from this one spot, essentially, right? And it might be advantageous to find out what the resultant force is, right? So instead of, if we didn't have 3 ropes, if we only had 1 big rope, right, pulling it, what would be the equivalent angle, right, that we should pull it to get the same like action? And what would be the equivalent force, right? So that's what a resultant force is. It's like in Photoshop, for example, if anyone uses Photoshop, or like any sort of software with layers, it's like grouping layers together. That's kind of how you can think about it, right? Yep. Okay, let's just, actually, I'll give you guys a short break. This will be a short tube, so I'll give you guys like a 5 or 10 minute break. And then, yeah, we'll get back to it. So yeah, just enjoy your break, enjoy the Smoko. Yes? What is it?
It's about modern technology.
Okay. Oh, is it actually?
Yeah.
Okay. You were trolling me.
How important is this system of? How important is it's not hard, but I just want to understand like what is the difference between cement composition and mineral composition?
What's up, Dom? That's my end 1300.
You're not even doing it right.
You got another issue.
But at least I'm actually
Cement.
So wrong. But yeah,
Drink it. I'll expired.
Oh, so you're just replacing so you're using this and you're subbing calcium oxide into your skin. That's so bad. Okay. And if you go a new name, fucking ally. But if you want to do it in which I think is more moral. What's past that?
No, but you laughed at your dad.
What's pasta in Paris? It takes super long to set. Oh yeah, anyways. You said I've got no wedding, that's on the like, so you said chips and blue balls of concrete, slow speed reaction. So what speed is your reaction? Makes it slow down or speed up. Oh, the reason is ordinary OPC, right? What you're learning about you're actually on the very far end of type of conference. Some flight action. Sort of like chicken eggs, or use like duck eggs. Oh, okay. But we only do ordinary like policemen, right? You do the okay, so wait, when we do structural calculations, do we have to calculate, do we have to account for like concrete? How long it takes to set? That's actually I think the designers tell you like I think the designers tell you the strength of the flight with the whatever matches the strength. No slump. Infinite slump.
Alright, let's just alright guys, we're gonna get started again very soon. Let me just, yeah, this is recording. Okay. Sorry, I'm just getting my notes up. Okay, so basically, the way that this works, I guess, is that in your middle, right, you'll have a workshop document that has a bunch of practice questions, and then the solutions will be released very soon for those. But at least for the first week, I actually don't like those questions. So I don't think they're as clear for explaining things, like from the basics, as some of the questions that I've ripped from the MEC booklet, basically, right? And so I'm going to teach you it from this, and then you can always go back and practice with those workshop questions as additional supplementary material, right? Okay, so let's look at this question first. Essentially, right, you'll come to learn soon that this little this free body diagram. Oh, it's not a free body diagram. Okay, basically this little like section that we're looking at, right, is part of a bigger structure. It's part of a truss structure. So you'll come to learn what that means soon. But all you need to know for now is that trusses, they're generally made out of steel or timber. I think this one might be made out of steel. And what does it say? Yeah, okay, whatever. Let's say it's made out of steel. And those members can take on tension and compression forces, right? So all like the information that it's telling us right now is that this member, right, this one in the top left, this member is in compression, right? And this member is in tension, okay? So those are the two structural members that they're referring to, but they're actually truss members, yeah? We have this joint O, right? And we have to calculate the forces on joint O and determine, actually, yeah. Basically what we're doing in this question, sorry, is we want the magnitude of the resultant of the two forces and the angle which makes that it makes with the positive x-axis. So that second part, that second sentence there is actually what we're looking for. Okay, so if you recall just before the break what I was talking about, it's to do with grouping together these forces and what angle that makes with some sort of axes. In this case, it's the positive x-axis, right? That's what we're going to be doing. Okay, so what does this look like? So we can use Newton's first law. Okay. So this will look a little bit different. So Newton's first law that you've probably seen in the slides, right? It'll say something like that. Sum of the forces is equal to 0. This is called static equilibrium, but it's actually not what the question calls for. Because what we're doing is using Newton's first law the second way, which is you can use it to group together a resultant force, right? And the reason for that, I'll get into it when we touch on types of forces, is there's things such as external forces and internal forces, and it depends on the perspective that you're looking at, okay? Right, so we're just looking at only external forces in this case, and so we're just going to group together all those external forces. Okay, sorry, that was a lot of talking, but we're just going to group together all the horizontal forces, right? And we're just going to call it Rx, okay? So, what horizontal forces do we have? We have this diagonal, we have two diagonal forces essentially, and we can break them up into the components like this, right? Yeah? Okay, so for the one on the left, for the compression member, right? The magnitude is 3. This is 3 kilonewtons, right? So we're doing everything in terms of kilonewtons. Okay, but we have this little triangle, this right angle triangle, and this is actually, I guess if you haven't done engineering studies, you probably haven't seen this before. This is called a Pythagorean triple, right? For a Pythagoras triangle, the ratio of these essentially works out. So if one side's 3, the other side is 4, and the hypotenuse is 5. This is just some ratio that we know, and I'll show you how it works in terms of when we're looking at just like a horizontal component of a force or just a vertical component of a force. So in this case, we're looking at just the horizontal component of this force. So what we do is we take 3 on the top of the fraction over 5. 5 is the hypotenuse, okay? What this means is that for the diagonal, which has a magnitude of 3 kilonewtons, right? We only want 60% of that, 3 over 5, right? We want 60% of that. That makes up the horizontal component of that diagonal. Does that make sense? Yeah? And the vertical component would be 80%, because it would be 4 over 5, right? Because the diagonal component has to be the biggest component. The hypotenuse has to be the biggest component, right? Anyway, so that's how it works. So next we look at the force on the right. That's got a magnitude of 2 kilonewtons, yeah? And now we have to, so what we know is that this angle is 30 degrees, right? And so we have to use our understanding of trigonometry to figure out the horizontal component, yeah? We're finding out the fx component essentially, right? So we use cosine 30 degrees, right? So it's like 30. We're looking for that component there. So that works out to be cosine 30, right? Again, this is like a ratio kind of thing. So cosine 30, you'll find that this number is less than 1, but above 0. It's going to give you a portion of your diagonal. Okay, great. When we add this together on the calculator, that's going to give us 3.53 kilonewtons. that is the first part of our question. Next, we do the sum of the vertical forces, right? We'll call it Ry. Okay. Here's where it gets a bit more interesting. So we're looking at this compression member, right? And we're looking at just its vertical force, right? Its vertical component, rather. Is this going to be positive or negative? Very good. So it's going to be negative. Why is that? Exactly. So since the arrow is down and right, and we're looking at just the up-downness, right? Down is a negative, right? Yeah. So this will give us a negative number. So we take the negative of its magnitude, which is 3. And do you remember what I was saying earlier about this Pythagorean triple? What portion of this diagonal vector is going to be carried out in the downwards direction? 4/5. 80% of that diagonal is going to act as its vertical component, right? Exactly. So 4/5, great. So I'm going really slowly, and if you've done engineering studies, you've done physics, you feel like, oh, why is he going so slowly? But I promise, when I go through something this slowly, I'll only ever do it once. So I'll speed up as we go, yeah? Okay. Next, we're looking at this tension member, right? The one on the right. Magnitude will be positive because of what we said. So it's going up, so now it's going to be positive. And instead of cosine 30, it's going to be sine 30, yeah? Because now we're looking at that component, yeah? The Fy component, vertical component of that diagonal force. Okay. So that gives us, once we solve it in the calculator, negative 1.4 kilonewtons, yeah? Great. Okay, but the question calls for the magnitude of R, right, of this resultant force. And all we've done is we've grouped together the horizontal component and the vertical component. So what might we do to get this resultant force, given that we have the horizontal and vertical component? So say we have a negative Ry like that, and it's that big, and we have a positive Rx like that, right? We want this diagonal R. So what formula can we apply to get there? Yeah, perfect. Pythagoras. So R, right? I might do this in absolute value here. This is just plug in Pythagoras theorem. Right? You sub in these numbers. So this one's 3.53. This one's okay. So you can sub in your calculator negative 1.4. You can also sub in 1.4 because it's going to square root it, so it'll take the magnitude anyway. This will give us 3.8 kilonewtons, yeah? Okay, great. Next, we're going to do the angle, right? And the angle formula, if you remember, was the tan inverse rise over run, right? And since we're dealing with this butterfly angle, right, it's going to be the normal way around, Ry on Rx, yeah? That'll give us tan inverse negative 1.4. Here's where the whether it's positive or negative will matter, right? So you got to make sure that's a negative there. This gives us negative 21.6 angle. So if you get a negative angle, right? Do you have a think about what that means in terms of what it'll look like visually? So basically, if you get a positive angle, it's going to go from the positive x-axis and upwards. If you get a negative angle, that's just going to mean positive x-axis downwards, yeah? So that's that angle there. So it goes down. So that will be some sort of negative, whatever. Okay. Okay, does anyone have any questions to do with how that question works? Okay, cool. Great, so moving on to question 2. So now there's another concept to kind of think about, and that's because we're dealing with a support of such. So we're going to be talking about supports a bit more, maybe either next workshop or the workshop after, I can't quite remember, but we'll be talking about them soon. But the idea is that, okay, here's how the question works. So we have this timber board or something with a spike that's embedded into it, and then we have 2 ropes pulling off of it, right? This is kind of weird. Like, I've never seen this in any other question, but this block is just some sort of intrusion, or like something that's blocking the rope, right? And what it's saying is the rope is angled perfectly so that it's not touching this block. Yeah, so it's really weird, but the only reason they tell us this is because it will help us determine the angle of the ropes, right? Yeah, just a real life application, I don't really know, but yeah. Okay, the other thing to note is that we have this reaction that, because as we said about supports, right, it's anchored into the wall, so we assume that it doesn't move, right, assuming it doesn't break, all that stuff. So it's gonna want to react to whatever force, external force that's pulling it. It's gonna have this kind of reaction force. So that'll be angled towards the wall in order to create this equilibrium. Like it's called static equilibrium, basically, right? It has to be angled that way, because if it was angled to the right, then it'd be moving, essentially, right? So all of these arrows have to kind of counterbalance each other so that they're not moving, right? Okay, does anyone have any questions about that? Okay, so the first step will be to find the angles which are associated. So it's not very well illustrated here, but we're trying to find these angles, right? Again, it's weird because it's to do with this rectangular prism extrusion thing, which, yeah, is a bit weird, but that's the angle that we're talking about, right? Okay, so let's draw it out. So we're going to use geometry. This horizontal like dimension, I guess, will be 200 mil. And this is 100 mil based on this. And our other shape is this one. We have another angle going on here. This is 200 mil. This is 150 mil, okay? Yeah, so we're going to use our formula for tan inverse, rise over run. Right, when we punch that into the calculator, we get 26.57. That one's not a problem. For the second angle, right, do tan inverse. Here's where it differs very slightly from the first question. Oh, sorry. I'm just going to write this as a positive number instead of a negative number, but I'll tell you what implications this has. Okay, that gives me 26.87. Okay, so if you recall in the previous question, right, I gave this a negative number and it gave me a negative angle output, right? And I was talking about how a negative angle refers to kind of like a decline angle from the horizontal plane, right? Okay, here what I've done is I've plugged in a positive number for this geometry, right? And that outputs a positive angle, right? In the end, both in an exam or setting will give you the right answer. The idea is this is to do with the perspective that you're referring to. And so if I want to call both these angles positive angles, then I can. It's fine. Does that, yeah, sorry. I kind of went on a little tangent there. But does that make sense? Both answers would be acceptable, that's what I'm saying. Okay, but the reason is because I just liked working with positive angles a bit more, so we'll just keep it as a positive number. Okay, so next we're going to do the force equilibrium. So Newton's third law is the free body diagram law, and I'm just going to quickly, briefly explain that now. Basically, if we're analyzing some sort of physics system, right, like technically there's a pull from the moon and the sun and whatever, like gravitational pull, but it's negligible, right? So there has to be some sort of like cap that you put on your system to analyze it. that's what a free body diagram is. It allows you to kind of just take this cut and only look at a certain section of a physics problem so you can analyze it, and in saying that the physics will work out if you account for all of these forces within the system, right? So, in other words, we just have a bunch of arrows, which is great. So now we're going to solve for these arrows because they're in an equilibrium, they're not moving, right? Okay. So I'm going to, okay, actually, well, I've kind of given the answer away. Basically, if we look at our free body diagram closely, right, the two static equilibrium laws that we've learned so far are some of the forces in the y direction and some of the forces in the x direction, right? And one of these will actually give you, like, lead you to the correct answer, and the other one's gonna slow you down, right? And this is to do with the amount of unknowns that you're gonna be checking, right? So we have two unknowns. We have tension, the tension of the spike, and we have P, which is some sort of pulling force on that rope, right? And some known pulling force on the second rope. So should we take the sum of the forces in the vertical direction or the horizontal direction? Just have to think about that for a second. What we should do is we should start with the sum in the vertical direction, okay? The reason for that is this pulling force is going to give you an unknown, and it's going to have a vertical component, right? And we have a known vertical component for the second pulling force. But for the tension in the spike, because of how we've cleverly set this up, this isn't going to be involved in our sum of the vertical forces equation at all. So even if we have two unknowns, we effectively only have one if we use this equation, right? I'll show you what I mean by that. So we take the sum of the forces is equal to 0 in the y direction. Let's look at this top right force first. That's unknown. That's going to be sine theta 1. And we're going to subtract the downwards component of that pulling force, right? But we don't have any vertical component for tension, right? So now we're just narrowing it down to one unknown. We can definitely solve for this. So we solve for P. We rearrange it by doing this. Sorry, my handwriting's kind of shit. Okay. And now we actually know what P is because we've done this in this order, right? Great. So now, when we take the sum of the horizontal forces, right? So previously, if we took the sum of the horizontal forces, we would be left with two unknowns, yeah, tension and the pulling force. Now, since we know that the pulling force is going to look like this, negative T, because it's not a diagonal arrow, it's entirely in the horizontal direction, so we're not going to deal with angles for this force, right? P cos theta 1, P cos theta 2. So those are the horizontal components now that we're looking at for these two. That's that and that, right? Since we know P, right, and we know the angles, which are 36.57, 36.87. Let me just sub these in as well. Yeah? So now we just have one unknown to solve for, which gives us this answer. So essentially this question is kind of the crux of, well, these first two questions which I've shown you, is kind of the crux of what this week's all about, right? And if you go to the civil schools bank of questions, I guarantee you can do pretty much most of them, just based on this understanding. I think there's probably one like unit vector or two unit vector questions that you can also figure out. But yeah, you'll have an understanding of tension, which is important, and know how to do like grouping together resultant forces, right? And you'll know how to do the force equilibrium method, which is what I just showed you now, right? That's great, but I'm gonna also go over two additional questions, but I promise they won't be very long. Oh, sorry. I'm gonna go over a little bit of theory and then two kind of shorter questions. Those two questions I'm gonna go over kind of like adjacent topics, which will build on your understanding. But the crux of it was in these first two questions I just showed you, right? Okay, if we want to get a bit more theoretical, right, we have different types of forces. And when we're looking at a force system, so like in terms of Newton's third law, we're analyzing whatever physics problem. We're going to have internal forces and we're going to have external forces, and then we kind of have names for these, right? So internal forces we call reactions, and external forces we call loads in the context of structures, right? So if you ever hear these words, what they mean is this. They're essentially internal and external forces, right? So if I push against this wall, I'm giving it an external force, right? It's just my body's mechanical energy or whatever. And the wall is pushing back to me because it's stopping the movement, right? Like it's staying still, and it gives a normal force back to me, right, when I push against it, and that's called a reaction. So that would be an internal force on the wall. Okay. Again, this is theoretical. This is another perspective you can look at forces from. We have body forces and contact forces, right? So body forces act on the entire volume of an object, and probably the one that's most relevant to this course that you'll see everywhere is weight. Basically, every building you have to consider gravity, which is, permeates the whole universe, whatever. Weight will always be there. It's probably the primary load that you're going to be looking at, and that acts throughout the entire volume of an object, right? The second one is buoyancy. So you probably won't deal with this until fluid mechanics if you're doing that. But yeah, buoyancy is like what causes boats and stuff to float on the water. Contact forces. Okay, here's where I'm going with this, right? We have the normal force and friction force, which are related to contact. So what this means is, say my hands are rubbing against the whiteboard, for example, right? That's not due to the entire volume of my hand. That's just due to the contact, the surface area between my hands that's acting on the whiteboard, right? So therefore, it's a contact force. Same with the normal force. It's a function of me pressing against it, right? It's distributing that load out based on its area, right? Okay, so once you have a understanding mainly of weight, weight, normal force, and friction force, right? Because I'm going to be using these words a lot in the next two questions, yeah? Oh, sorry. Does anyone have any questions to do with this? Yeah.
Tension force concept?
Okay, so that's a very good question. So this is more like, sorry, are you doing civil engineering, mechanical engineering? Okay, so you will do mechanics of solids, and you'll understand this a bit further. But essentially, it's under contact forces, and the reason for that is for a rope, right? This isn't really in the course. It's kind of outside the scope of this course. You might have seen stress before. Axial stress is a function of the force divided by the area. This is the cross-sectional area, right, of this rope, right? And so this tension force is your force. Yeah, basically, in short, it's under contact forces. But just for my explanation, it's not as clear to include tension because it's kind of outside the scope of the course, so I didn't include it. But yeah, for your curiosity, that's it. Yeah. Does anyone else have any questions? Cool. Okay, so basically, here's something slightly new. We don't always use the XY plane. And oftentimes when you have a question that's on an incline or like a slope, basically, it might be better to refer to things in terms of the normal and tangential forces instead, right? So the tangential plane is that one. That refers to along the slope and along the incline. And the normal force is perpendicular to this. So this is kind of a new coordinate system that we're using. So again, instead of X and Y, right, it's actually better for certain questions to use this 2D coordinate system. That's what we call it, right? Okay, Because we know that the tangential component of the force F, right? So if we're looking at it in terms of this, this is like a diagonal vector, right? We're told this component, which is tangential with the plane, the inclined plane, let's call that Ft. We know that's equal to 75 newtons, right? What we're told is, okay, what's the magnitude of that diagonal? Determine the magnitude of F, and also determine its n component. That's the component that's perpendicular to the plane. That's what the question's calling for. Sorry, I've kind of drawn over this. This angle that's written here is 10 degrees. Yeah? And then this angle that's written here is 30 degrees, right? So we just need to kind of, we just need to think about it in terms of how do these angles combine to make this system. So if we tilt our heads, what does it look like? Okay, so it turns out it looks like this, essentially. This angle ends up being 40 degrees, right? So you add this angle, actually that it's to do with Z angles. So if you remember from maths, these are equivalent angles, so that 30 degrees there ends up being this 30 degrees here, and then that 10 degrees adds on like that. So that total angle becomes 40 degrees, right? And that's where our F is coming from. Yeah. Okay. Anyway, it ends up being like this, right? Oh, sorry. Let me find a good spot for this. Okay. Let me just reiterate that the tangential force was 75 newtons, right? Another way to put this is 75 newtons, right, is equal to F cos 40, right? So this force, right, we were told was 75, and that's the horizontal component of this diagonal force, right? So when we rearrange it, this magnitude, we solve it by dividing 75 onto cos 40. That gives us 97.91 newtons, yeah? Okay, that's the first part of the question. That's just asking for the magnitude, right? Next, we solve for this component, that's the normal component. And that's quite trivial once we have the diagonal, right? And that's because we know that this diagonal, that one, is 97, whatever. Yeah, everyone following along? And so we can use, so that would be the same as doing it from there, using this butterfly angle, right? Yeah. And that gives us, so we want to sub in F. That gives us 62.94 newtons. So that's the second part of the question. Okay. Sorry, I didn't do the cleanest explanation there, but does that make sense? Yep. Does anyone need, I can do it again at the end. I can go up to my QR codes, but if anyone needs the folder again, I'll just scroll up to the very end so you can look at the notes after class as well. Okay. So for our last question here, that's okay. So for our last question here, we have a block which is being pulled, so that's in tension, right, by some sort of, it's not a rope, but yeah. So it's being pulled, and we're given this information about the ground, right? So this is the static and kinetic friction constants. So you might recognize this from physics, right? to kind of explain what they are, again, it's kind of dumb, but I'm just going to do it. Right. So if I have this chair, right, I want you, right? If I tilt this, right, what's stopping my shoe from falling off is the static friction. That's because it's not moving yet, and so whatever the two materials, the sole of my shoe and the chair, have, they just have some known constant static friction. I can keep tilting it until the shoe falls off, right? Yep. So static friction helps to calculate that threshold number before the shoe slides off, essentially, right? What kinetic friction is like if I have my shoe and I'm rubbing it against the ground and it's moving, right? My shoe makes a scraping noise, right? It's kinetic friction because it's already in motion, but it's scraping against the ground, and so the ground's going to give it some kind of resisting force. It's called kinetic friction force, right? So, yeah, that's what the difference is. But in the statics portion of this course, we only care about static friction. So essentially, this block isn't moving yet. So let's read the question. The 700 Newton force is applied. That's that pulling force to a 100 kilo block, right? And it's stationary before this force is applied. Determine the magnitude and direction of the friction force exerted by, horizontal surface onto the block. Okay. So first we start with a free body diagram, yeah? Let's draw the shape. So that's that block there. The block will have a self-weight, right? And we can find the weight force with mg, right? The mass we know is 100 kilograms, right? And gravity, in this course we take it as 9.81. In other courses it might be 9.8. If you do when you do concrete structures, it's 10. They get more and more lazy as engineers, right? As you progress through your degree. Okay, so that gives us that the weight is 981 newtons, yeah? Next, so generally how steps go is we start with the weight force because we're usually given the weight of the block. That's what we know the most information about, right? Next, we're going to calculate the normal force, okay? And because this block isn't being yanked, right, like off the ground, it's not supposed to move up and down, it's not supposed to fly, right? We know that the normal force is actually just going to counterbalance the weight exactly. So it will be equal in magnitude. Okay, wait, no, that's a lie. Ignore what I just said. Okay, basically, right, let's look at all the vertical forces actually, because we have a pulling force. So we have a pulling force of 700 newtons, right? And we also have a static friction, which acts on the surface, right? Okay, so now we have all the forces in place. Before I say anything wrong, we have to look at just the vertical forces in order to get the normal force in this particular case on a flat ground, right? So what the normal force is essentially the remainder after you take the weight and the vertical component of that pulling force. Does that make sense? So the normal force will be less than the weight force because that pulling force is going to partially remove that counterbalance, right? Oh, also, if you ever see the word slip, it's referring to kinetic friction. If you see the word no slip, that means static friction. Yep. So we take the sum of the vertical forces. Yeah. And yeah, now we're just simply going to calculate n because that's the only unknown that we're looking for, giving us 631 newtons, yeah? Sorry, it might get confusing at times because n I'm referring to normal force, but n I'm also referring to newtons. So it's kind of contextual. So in this case, on the right hand side will be newtons, left hand side would be, yeah. Okay, that makes sense so far, right? Okay, basically, there's a formula that we know for the max friction force before a slip occurs, right? And that's, you take the static friction coefficient, right, and multiply it by the normal force. That's not newtons, that's normal force, right? So it's a function of the normal force. How this might make sense is if you think about, you wrote something on a paper with a pencil, right? And you lightly rub it out. Say it doesn't rub out, right? So what are you going to do? You're going to press down on it harder and rub out, and that gives it more normal force, which gives more friction force, and then the pencil will come off, right? Yeah. So that's why friction force is a function of your normal force, actually. Okay. So this was given. This was a material property that was determined probably through testing or whatever that they did. And we solved this first part. That's 631 newtons for normal force, giving us 505 newtons for, this is the max allowable static friction before, and if we go over it, we're gonna slip and move, basically, right? And next we're gonna take the horizontal sum of the forces. Okay, so if we look at our free body diagram again, what does this mean? This means that we're only gonna look at the friction force and the horizontal component of the of the pulling force, right? So that's exactly what we'll do. Yeah. Okay. Basically, that leaves us with only one unknown that we can solve for, right? Yeah, 606 newtons. Okay. So here's what I've done. I've called this FF because it's a variable. We solve for it separate to what the max friction force is, okay? And so that's named differently to Fs max. So basically, our threshold number was 505, which is what we calculated based on the normal force and the material properties, right? What we ended up finding that our friction force was 606, right? And what that means, right, is because our friction force exceeds our threshold, that means we actually have movement. It's actually going to be moving, yeah? Oh, sorry. Yes. Yeah. Okay. Let me just write it out and then I'll explain it. I'm trying to explain like two things at once. Yeah. So when we do use the formula for kinetic friction, we get that. Okay. What this means is that we are technically in static equilibrium. So here's where it gets a bit confusing. We're in static equilibrium because the sum of the forces is equal to 0, but there's no acceleration, right? So what we've ended up with our situation with is, pretend our box is this jet, right? And maybe it doesn't have wheels, so it has a bit more friction at the bottom, right? And I have a rope that's pulling it like this, right? We're moving at a constant like speed and all that, so there's no acceleration on the system, so it's technically in static equilibrium, but it's moving, so there'll be a kinetic friction force as I'm pulling it and moving at a constant velocity. Sorry, this will make more sense as we touch on the dynamics part of the course, but just trust me for now, basically, right? Yeah, so we have a friction force in the left direction of that much, right? If we want to visualize it on a graph of what I was just yapping about, it looks like this. Our threshold number is 505 newtons, yeah? That's up until that point, nothing will move, and then we'll have this reaction force that counterbalances everything. But where we ended up was over here, okay? Maybe like something like here. It had this much applied force, so we ended up here. And the kinetic friction force in this course we assumed to be like a flat number. So yeah, I'm not going to overcook that explanation. So it looks something like this. This was determined based on our static constant multiplied by the normal force, and this one was determined with the kinetic multiplied by the normal force. And the kinetic friction you'll find is always less than or equal to. Okay. The static one will always be greater than, basically, than the kinetic one. So it'll be always be lower. The graph will always move down, or if they're equal, then the graph will look like that. So anyway, okay. That concludes my class. Again, yeah, it was a bit of a short one, but hope you enjoyed. Okay, you don't need to clap. Okay, well, what I'll do is I'll scroll up to the top, and then yeah, if you missed the attendance, it's on the left. My notes, copy of my notes on the right. Yeah, there'll be a recording. I'll let you know how to access that from next week onwards. If you have any questions, just come up front. Happy to answer them. But yeah, that's it.